Dear students, now we are going to learn about elementary properties of non-Abelian groups. In last module, we learned some elementary properties of Abelian groups. In this module, we are going to learn about non-Abelian groups. In particular, dihedral group and symmetric group. Now, let's start with definition of non-Abelian group. A non-Abelian group, a group that is G is the element in which there exists at least one pair of elements and A and B of G such that A into B is not equivalent to B into A. Let's find out what are the examples of non-Abelian group. One of the simplest examples of a non-Abelian group is the dihedral group. Let us see the dihedral group. An important family of examples of non-Abelian groups is the class of groups whose elements are symmetries of geometric objects. The simplest subclass is when the geometric objects are regular planar figures. For each n is the element of Z, where n is greater than or equivalent to 3, let D of 2n be the set of symmetries of a regular n-gon, where a symmetry is any rigid motion of the n-gon which can be effected by taking a copy of the n-gon, moving this copy in any fashion in 3 space and then placing the copy back on the original n-gon. So, it exactly covers it. More precisely, we can describe the symmetries by first choosing a labeling of the n vertices. Please see the figure. Then, each symmetry S can be described uniquely by the corresponding permutation sigma of 1, 2, 3 and up to n, where if the symmetry S puts vertex I in the place where vertex j was originally, then sigma is the permutation sending I to j. For instance, if S is a rotation of 2 pi by n radians clockwise about the center of the n-gon, then sigma is the permutation sending I to I plus 1. For 1 is less than or equivalent to I and it is again less than or equivalent to n minus 1 and sigma n is equivalent to 1. Now, make D of 2n into a group by defining St for S, T is the element of D of 2n to be the symmetry obtained by first applying T. Then S to the n-gon. Here note that we are viewing symmetries as functions on the n-gon. So, St is the just function composition. If S, T affect the permutation, that is sigma and tau respectively on the vertices, then St affects sigma or tau. The binary operation on D of 2n is the identity symmetry which leaves all vertices fixed, denoted by 1. And the inverse of S is the element of D of 2n is the symmetry which reverses all right motions of S. Now, we shall going to see about the properties of the elements of dihedral group. The first one is 1 or r square up to r to the power of n minus 1 are all distinct and Rn is equivalent to 1. The second step is S square is equivalent to 1. And the third step is S is not equivalent to I power of I for any I. For third step, S is not equivalent to R power of I for any I. And fourth step is SR to the power of I, which is not equivalent to SR to the power of J. For all 0 is not less than or equivalent to I, and J is less than or equivalent to n minus 1 with I is not equivalent to J. And the fifth one, that is final step, or S is equivalent to S or inverse. In general, R to the power of I S is equivalent to S R to the power of minus I. For all 0 is less than or equivalent to I, and which is again less than or equivalent to n minus 1. So, we fix the rotation of d of 2n as d of 2n is equivalent to 1 or r square up to r to the power of n minus 1, and s, sr, sr square and up to sr to the power of n minus 1. First, let us see how to find the product of two elements in D of 2n. For example, if n is equivalent to 4, that is in D of 8 is equivalent to r square into r cube, that is equivalent to r power of 4 plus 1, that is equivalent to r. SR into SR square is equivalent to S into RS into R square, that is equivalent to S into SR to the power of minus 1 into R square, which is again equivalent to S square R, that is again equivalent to R. SR square into SR is equivalent to S into R square S into R, which is again equivalent to S into S R to the power of minus 2 into R, which is again equivalent to S square R inverse, that is again equivalent to R cube. Now we construct the complete Cayley table of D of 8. Please view the board, students. Here the order of R is 4, order of R square is 2, order of R cube is 4, and order of S is 2, and order of SR is 2, order of SR square is 2, and order of SR cube is 2. Recall that a subset S of elements of a group G with the property that every element of G can be written as a finite product of elements of S and their inverses is called a set of generations of G. We shall indicate this rotationally by writing G, that is arrow bracket S, and say G is generated by S or S generates G. Now we find the generator set of D of 2n. In D of 2n we have relations, it is r to the power of n is equivalent to 1, S square is equivalent to 1, and RS is equivalent to S R inverse. Moreover, in D of 2n, these three relations have the additional property that any other relation between elements of the group may be derived from these three. Therefore, one presentation for the dihedral group D of 2n using the generators is D of 2n is equivalent to or less than R, S, that is proportional to r to the power n is equivalent to S square, that is equivalent to 1, or S, that is equivalent to S R inverse. The dihedral group of order 2n is often called the group of symmetries of a regular n-gon. In this notation, the group of symmetries of an equilateral triangle is the dihedral group D of 6 and is the smallest non-Abelian group with 6 elements. Next, we shall move on to another example of non-Abelian group, that is general linear group. Denote M2R is a set of all 2 into 2 matrices. Let GL2R be the subset of M2R consisting of invertible matrices. That is, matrix A is equivalent to ABCD is in GL2R if there exists a matrix A inverse such that A into A inverse is equivalent to A inverse into A, which is again equivalent to I, where I is the 2 into 2 identity matrix. For A to have an inverse is equivalent to requiring that the determinant of A be non-zero. That is, determination A is equivalent to AD minus BC, which is not equivalent to 0. The set of invertible matrices forms a group called the general linear group. The identity of the group is the identity matrix. I is equivalent to I0, 0, 1. The inverse of A is the element of GL2 or is A inverse is equivalent to 1 by AD minus BC into matrix D minus B minus C A. The product of 2 invertible matrices is again invertible. Matrix multiplication is associative, satisfying the other group axiom. For matrices, it is not true in general that AB is equivalent to BA. Hence, GL2 or is a non-Abelian group. In particular, the set of all invertible matrices having determinant 1, then will it be a group? The answer is yes. It is a special linear group and it is denoted by SLNR. Let's see briefly. Now we are going to see briefly the special linear group. Let SL2R be the subset of GL2R consisting of matrices of determinant 1, that is, a matrix A is equivalent to ABCD is in SL2R exactly when ADBE is equivalent to 1. To show that SL2R is a subgroup of the general linear group, we must show that it is a group under matrix multiplication. The 2 into 2 identity matrix is in SL2R as is the inverse of the matrix A. A inverse is equivalent to D minus B minus C A matrix. It remains to show that multiplication is closed, that is, that the product of 2 matrices of determinant 1 also has determinant 1. Let A is equivalent to matrix A, B, C, D into B is equivalent to matrix E, F, G, H with AD minus BC is equivalent to 1 and EH minus FG is equivalent to 1. Then AB is equivalent to matrix AE plus BG, AF plus BH, CE plus DG and CF plus DH. Now AE plus BG into CF plus DH minus AF plus BH into CE plus DG is equivalent to ACEF plus ADEH plus BCFG plus BDGH minus ACEF minus BCEH minus ADFG minus BDGH, which is again equivalent to AD into EH minus FG minus BC into EH minus FG, which is again equivalent to AD minus BC into EH minus FG, which is overall equivalent to 1. Therefore, AB is the element of SL2R, and so SL2 of 2R is a group. The group SL2R, it's called the special linear group. Now let us see the remark. The set of all 2 into 2 matrices M2R forms a group under the operation of addition. The 2 into 2 general linear group GL2R is a subset of M2R and is a group under matrix multiplication, but it is not a subgroup of M2R. If we add 2 invertible matrices, we do not necessarily obtain another invertible matrix. Observe that matrix 1 0 0 1 plus matrix minus 1 0 0 minus 1, that is equivalent to matrix 0 0 0 0. But the 0 matrix is not in GL2R. Quaternion groups are one another example for non-Abelian group. Quaternion group, let 1 is equivalent to matrix 1 0 0 1 and I is equivalent to 0 1 minus 1 0 matrix and J is equivalent to matrix N I 0 and J is equivalent to matrix 0 I 0. K is equivalent to matrix I 0 and 0 minus I, where I square is equivalent to minus 1. Then the relations I square is equal to J square, which is again equivalent to K square, that is equivalent to minus 1. Ij is equivalent to K, Jk is equivalent to I, Ki is equivalent to J, Ji is equivalent to minus K, Kj is equivalent to minus 1 and Ik is equivalent to minus J hold. The set Q of 8 is equivalent to plus or minus 1 plus or minus I plus or minus J and plus or minus K is a group called the Quaternion group. Notice that Q of 8 is non-commutative. Therefore, Q of 8 is a non-Abelian group. Next, we shall discuss briefly about the symmetric groups. Next, we shall briefly discuss about the symmetric groups. Symmetric group S of n. Let capital omega be any non-empty set and let S of capital omega be the set of all bijections from capital omega to itself. That is the set of all permutations of capital omega. The set S of capital omega is a group under non-function composition 0. Note that 0 is a binary operation on S of capital omega, since if sigma is proportional to capital omega to capital omega and tau, that is proportion to capital omega to capital omega, are both bisection, then sigma 0 tau is also a bisection from capital omega to capital omega, since function's composition is associative in general. Omega 0 is associative. The identity of S of capital omega is a permutation 1 defined by 1 into A is equivalent to A. For all A is the element of capital omega. For every permutation sigma there is a two-sided inverse function sigma to the power of minus 1 capital omega to capital omega satisfying sigma into 0 sigma to the power of minus 1, that is equivalent to sigma to the power of minus 1 into 0 into sigma, which is equivalent to 1. Thus, all the group A into A of M1 plus 1 axioms hold for S of capital omega into 0. This group is called the symmetric group on the set capital omega. It is important to recognize that the elements of S of capital omega are the permutations of capital omega, not the elements of capital omega itself. In the special case, capital omega is equivalent to 1, 2, 3 and up to n. The symmetric group on capital omega is denoted by S of n, the symmetric group of degree n. First, we show that the order of S of n is n factorial. The permutations of 1, 2, 3 and up to n are precisely the injective functions of this set to itself, because it is finite and we can count the number of injective functions. An injective function sigma can send the number 1 to any of the n elements of 1, 2, 3 and up to n, that is proportional to sigma of 2, can then be any of element except sigma of 1 or sigma of 2. Sigma 2 can then be any one of the elements of this set except sigma 1. So, there are n minus 1 choices for sigma 2, that is proportional to sigma 3, can be any element except sigma 1 or sigma 2. So, there are n minus 2 choices for sigma 3 and so on. Thus, there are precisely n minus 1 minus n minus 2, that is up to 2. 1 is equivalent to n factorial possible injective functions from 1, 2, 3 and up to n to itself. Hence, there are precisely n factorial permutations of 1, 2, 3 and up to n. So, there are precisely n factorial elements in S of n. We now describe an efficient notation for writing elements sigma of Sn, which is called cycle decomposition. A cycle is a string of integers which represents the elements of S of n, which cyclically permutes these integers and fixes all other integers. The cycle A1, A2 and up to Am is the permutation which stands Am to A1. For example, 2, 1, 3 is the permutation which maps 2 to 1, 1 to 3 and 3 to 2. In general, for each sigma element of S of n, the numbers from 1 to n will be rearranged and grouped into k cycles of the form A1, A2 up to AM1 into AM1 plus 1 into AM1 plus 2 and up to AMK minus 1 plus 1, AMK minus 1 plus 2 and up to AMK, from which the action of pi on any number from 1 to n can easily be read as follows. For any x is the element of 1, 2, 3 and up to n, first locate x in the above expression. If x is not followed immediately by a right parenthesis, that is, x is not at the right end of one of the k cycles, then sigma x is the integer appearing immediately to the right of x. If x is followed by a right parenthesis, then sigma x is a number which is at the start of the cycle ending with x, that is, if x is equivalent to AMI for some I, then sigma x is equivalent to AMI minus 1 plus 1, n where M0 is taken to be 0. We can represent this description of sigma by, students please see the diagram. The product of all the cycles is called the cycle decomposition of sigma. For example, let S of 3 denote the set of all 1 to 1 functions from 1, 2, 3 and to itself. Then S of 3 has 6 elements and they are: E is equivalent to matrix 1, 2, 3, 1, 2, 3, which is equivalent to 1 into 2 into 3, alpha which is equivalent to matrix 1, 2, 3, 2, 3, 1, which is equivalent to 1, 2, 3. Alpha 1 is equivalent to 1, 2, 3 matrix 3, 1, 2, that is equivalent to 1, 3, 2. Alpha 2 is equivalent to 1, 2, 3 and matrix 1, 3, 2, that is again equivalent to 1 into 2, 3. Alpha 3 is equivalent to matrix 1, 2, 3, 2, 1, 3, which is again equivalent to 1, 2 into 3. Alpha 4 is equivalent to matrix 1, 2, 3, 3, 2, 1, which is again equivalent to 1, 3 into 2. Now, let us construct a Cayley table for S of 3. First, let us compute alpha into alpha 2. Alpha into alpha 2 is equivalent to matrix 1, 2, 3, 2, 3, 1 into 1, 2, 3 and 1, 3, 2. Here in alpha 1 maps to 2 and in alpha 2, 2 maps to 3. So, in alpha into alpha 2 is proportional to 1 maps to 3. Again, in alpha 2 maps to 3 and in alpha 2 maps to 3 maps to 2. So, in alpha into alpha 2 is proportional to 2 maps to 2. Again, in alpha 3 maps to 1 and in alpha 2 1 maps to 1. So, in alpha into alpha 2 is proportional to 3 maps to 1. Therefore, alpha into alpha 2 is equivalent to matrix 1, 2, 3, 3, 2, 1. Similarly, we can construct the Cayley table as thus: S of 3 forms a group under function composition, but alpha into alpha 2 is equivalent to alpha 4 and alpha 2 into alpha is equivalent to alpha 3, and so alpha into alpha 2 is not equivalent to alpha 2 into alpha. Hence, S of 3 is non-Abelian. Now we shall see the symmetries of squares. We associate each motion to D of 4 with the permutation of the locations of each of the 4 corners of a square. For example, if we label the 4 corner positions as in the figure and keep these labels fixed for reference, we may describe a 90-degree rotation by the permutation. Permutation is equivalent to matrix 1, 2, 3, 4 and 2, 3, 4, 1, whereas a reflection across a horizontal axis yields pi is equivalent to 1, 2, 3, 4 matrix and 2, 1, 4, 3. These two elements generate the entire group. That is, every element is some combination of the P1s and Pi1s. When D of 4 is represented in this way, we say that it is a subgroup of S of 4. Now we shall see about the properties of permutations. Every permutation can be written as a cycle or as a product of disjoint cycles. Now let us see one by one. The order of a permutation written in disjoint cycle form is the least common multiple of the lengths of the cycles. Every permutation A can be expressed as a product of an even number of 2 cycles. If a permutation A can be expressed as a product of an even number of 2 cycles, then every decomposition of A into a product of 2 cycles must have an even number of 2 cycles. A permutation that can be expressed as a product of an even number of 2 cycles is called an even permutation. A permutation that can be expressed as a product of an odd number of 2 cycles is called an odd. The set of even permutation in S of n forms a subgroup of S of n. The group of even permutations of n symbols is denoted by A of n and is called the alternating group of degree n into A of n is a subgroup of S of n. I hope, students, you are all well versed in this chapter we have discussed so far. Thank you.